Barry?
Yes, Paul.
3, 2, 1, fire. This is a linear induction motor. It uses about 100 kilowatts, and it can accelerate 4-pound missiles such as this up to nearly 100 miles an hour. Ready again, Barry?
Yes, Paul.
Fire. This is a big motor. On the other hand, in this thimble, I have the rotors of over 10,000 electric motors. And nobody is going to deny that these are small motors. Now, a linear induction motor like this is an easy thing to understand because it's just like a flowing river. This is a river bed. If I dip a piece of wood into the river, turn on the water, the first thing that happens is that the wood floats. It rises up, and then when the river is flowing nicely over the weir, I let go the wood, and it soon attains the same speed as the water. If, on the other hand, I dip into the river a cylinder like this, which is free to spin, then the river spins it, and notice which way it spins. The water passing underneath it causes it, as it were, to roll backwards. Now let's look at this linear motor, which is just like a bit of the big machine we've just been seeing. And this is like a river too. In this case, I'm going to put in a magnetic piece of wood, which is a piece of aluminium. I turn on the current, which is like turning on the water, and the magnetic wood floats. When I let it go, it soon attains the speed of the river. But of course, in this case, the speed of the river is much greater than was the speed of the water. Again, if I dip a cylinder, this time a copper cylinder, into the magnetic river, it spins in the appropriate direction. We can have a shallow river. There is a shallow river. Or turn on some more water. There is a deep river. And when I'm making these comparisons, I'm doing what every engineer does almost every day of his life. I'm using an analogy. Now, a good engineer knows when to use an analogy and where it breaks down. And I'm going to show you where this one breaks down. If I take a heavy cylinder, such as this, and place it in the river, and then turn on the water, you see the flow rolls the cylinder downstream. If I now place the same cylinder in the magnetic river and turn on the magnetic water, it rolls upstream because you see the river is flowing that way. It doesn't matter whether I use a small cylinder or a long cylinder, and these are all of copper, or whether I use a steel cylinder, they all roll backwards. A steel ball rolls the same way. So does a steel washer. Of course, you can have a lot of fun with this. This all-plastic motor car has had 4 steel wheels fitted. There's the engine. And when you release it, it goes quite nicely. Now, why is this? Why do all these pieces of metal roll backwards along the field? To understand what's going on, we need to look at the shape of the field lines over this motor. They come from a north pole into a south, like that, and the whole field pattern is moving along, like the magnetic river. Now, suppose we could sit at one place over the machine, such as in that little square, and watch the field lines go by. Notice the direction of the arrows. At the moment, the field is to the left. Now it's upwards, to the right, downwards. Left, up, right, down. So it's left, up, right, down. And the rotation, you see, is clockwise, which is to say, rolling backwards. So the whole machine behaves like a mechanical rack and pinion, in which this is the field and this is the rotor. And here is the action. Well, of course, mechanical things are easy to understand. But when we make it magnetic, it's a little less obvious. But we put in a row of horseshoe magnets, and the action, as you see, is very similar indeed. This, then, we call a rack and pinion motor. Now, in a linear motor, a row of electromagnets effectively replaces the row of permanent magnets, and instead of the many-toothed wheel, I'm going to use a very simple wheel with just 2 teeth. When I switch on the motor, the wheel spins, and if I disconnect one of the wires to this motor, I can stop this travelling field dead, like that, and now we can see the shape of it. There is the field shape. If I draw the wheel slowly along the surface, you can see the rack and pinion action in slow motion in the stationary field. Now if I reconnect, I shall start the field moving again and spin the wheel. Now the rotary version of this machine is what drives an ordinary electric clock. It has a toothed wheel which moves inside a set of teeth on the stationary part. When I switch it on, there is a clock motor. Motors with steel rotors are purely magnetic machines because they don't depend for their action on any electric current flowing in the moving part. Unlike, for example, this copper cylinder. And when that spins, it does so because an electric current is caused to flow in the copper. And so I call this an electromagnetic machine. Now, by far the most intriguing magnetic machine for me can be made simply with an ordinary paper clip. First, I unroll it, and then wrap it around a pencil or other non-conducting rod, and then offer it to the linear motor. This spins very well, as you see, and yet there is clearly no electric circuit, so no current can flow in the clip. Now I want to distinguish very clearly between magnetic machines and electromagnetic machines. Both types are used extensively, both in industry and in the home. A washing machine, for example, uses an induction motor, which is an electromagnetic machine. Electric clocks, as we've just seen, are magnetic machines. Now, magnetic machines get better as they are made smaller, whereas electromagnetic machines are better as they are made bigger. This last fact I can prove to you in more general terms by using what I call my goodness models. Now, every machine has a magnetic circuit which I represent like this. The flux in that circuit is made to induce a current into an electric circuit which links it, like that. The force you can get from a machine is proportional only to the product of the flux in the magnetic circuit and the current in the electric circuit. So flux and current are the things you want lots of. The thing which stops you having as much as you'd like, of course, is the resistance in the case of the electric circuit and the magnetic resistance, or reluctance as we call it, in the magnetic circuit. The resistance of an electric circuit is proportional to its length and inversely proportional to its area. So if I take a second electric circuit, which is twice as big in every linear dimension as the first, then its length will be twice as great, but its area is 4 times as great. So the resistance of the big circuit altogether is only half the resistance of the small circuit. And when we put the 2 circuits together to make our machine, the combined effect of the 2 is to make the big machine 4 times as good as the small one. So it seems as if the rule for electromagnetic machines is that the bigger they are, the better they are. Now, with purely magnetic motors, the rules seem to work the other way around. Let me show you what I mean. These sheets are made of rubber, but it's rubber which has been impregnated with a magnetic material, and they've been magnetized so that the whole of that surface is a north pole and the whole of that is a south. And yet, there doesn't seem to be any measurable force between them. They behave as if they were unmagnetized. But if I take some scissors and cut two pieces from one of the sheets, then we see how those behave. There's no noticeable repulsion, but at least there's some attraction. And if I cut smaller pieces still, then at once there's attraction, and this time there's even some repulsion. Put one piece on top of the other with reverse polarity, and it just doesn't want to know the other one. So magnetic things get better the smaller they are. Now let's apply this principle of size to our fascinating racking pinion motors. I'm going to put a plastic tray on top of my row of coils, and I'm going to roll along its surface some split steel washers. A smaller one should go better still. Very lively. Now this experiment poses the intriguing question, just how small things can I roll? Can I literally spin an individual iron filing? Well, the answer is that I can. And to demonstrate this, I'm going to cover the entire surface of the motor with iron filings. And switch on, and you'll see what happens. Well, I don't know what you expected to happen. I know the first time I tried this, I certainly didn't get the result I expected. Look at the way the walls are forming. Walls of filings, spacing themselves from each other. The spacing between the walls depends on their height. So I can comb this lot like I could comb my hair. All I'm doing now is flattening the filings down, and as I do so, they get closer together. If you look at an individual wall, you'll see that the bulk of the filings in it are actually at rest. It's only the ones around the outside which are moving, and they're producing a gradual drift backwards along the field. Many of the experiments we've been doing with iron filings can be done with much simpler apparatus. For example, all you need is a horseshoe magnet and a means for rotating it. A plastic dish can be clipped over the magnet, and then into the dish we put a steel ball. When I rotate the magnet slowly, the steel ball just goes round opposite one of the poles. That isn't very exciting, nor is the fact that when I turn more quickly, centrifugal force flings out the ball to the sides of the dish. But if I rotate more quickly still, the steel ball will become a rack and pinion motor. There it goes, rotating backwards in the travelling field. Let's put some iron filings in the dish. Turn the handle and see what happens. At once we see the walls building up, and the backward rotation, and something else. Can you see the spirals of filings running up the hill into the middle? The inward movement of these filings implies there must be an outward travelling magnetic field to produce it. And if this is true, then it's very exciting indeed, because centrifugal magnetism, which is what this would be, is unknown at present. But if we turn the handle more slowly, and watch what happens in slow motion, we can see that the filings form into lozenge-shaped solids, and these are rolling over and over and spiraling into the middle, for the same reason that any rolling object traces out a spiral on a flat surface. So we hadn't made a discovery at all. But of all the phenomena we observed with the iron filings, the most striking, perhaps, is the building up of the walls. It tells us, among other things, that when we make a rack and pinion motor, we shouldn't use a solid cylinder like this. We should divide the cylinder into a number of discs. These 6 steel discs have been spaced to match the spacing of the walls in the iron filing experiment. They are going to wind up this cord, and in doing so, lift a 2-kilogram mass. The discs will spin at 3,000 revolutions a minute. That is a lot of power to extract from such a small amount of material. In fact, that rack and pinion motor produces more power for its size than any other type of hysteresis motor. The shape of those discs is very similar to the shape of a coiled spring. At least it is magnetically. The most recent research that I've been doing has been concerned with rack and pinion motors of this kind, where we put a very small spring inside a glass tube, because this could operate as a self-contained pump, a helical pump. This spins very nicely. And of course, smaller ones, being magnetic machines, operate better still. And I can spin this spring about 3 inches above the surface. Now, if I can develop these to the stage where they will be small enough to operate inside living tissue, then they could be very useful to the surgeon during operations. If this should be successful, then I'm never going to forget that it began with no more than a paperclip and a pencil. This, then, is the world of small motors. Now, I don't have to tell you that this is a big motor. In fact, in terms of diameter, it's one of the biggest made. Its rotor is this aluminium disc. So it's an induction motor, and therefore an electromagnetic machine. And in spite of the fact that the moving part is rotary, it is a test rig for linear machines. Let's have a look at the driving unit. This row of coils is a linear motor which has been bent slightly to fit the shape of the disc. The speed of the field on this motor is nearly 300 miles an hour. Now, motors of this kind are being developed to drive very high-speed passenger-carrying vehicles of the future. Now, to test such machines on an actual track would cost a very large sum of money. You'd have to build a track many miles long to get up to this kind of speed. But on this disc, we shall be able to get real speeds at the edge of the disc of nearly 300 miles an hour. So let's switch it on. Power on. But remember, whether it's a big, complicated piece of machinery like this, or if it's simply a paperclip and a pencil, in the world of motors big and small, the work you've just seen is only the beginning. As an engineer, or indeed any kind of scientist, it's a good idea sometimes to sit down
pour yourself a cup of tea and take a hard look at the things around you to see whether they have anything to do with your own work, even though at first sight they may not. Take this teapot, for example. Why is it the shape that it is? And is it the best shape for a teapot? Well, I'd like to show you the first teapot that was ever designed. You may think it was centuries old, but it isn't. It was designed in 1971. First of all, it's a rather gorgeous thing, isn't it? But that's one affair. Why do I say this is the first teapot ever to be designed? Well, let's look again at our old-fashioned teapot and see how we can criticize it. First of all, it holds a mass of tea, and the center of gravity of that mass is anywhere but near your hand, so all the time you're fighting against gravity. Then, if it had been a large teapot, I would have to put my finger under the spout, in fact, to hold the weight at all. You've probably seen ladies do this in large canteens. Then you tend to scald your finger. When it pours with an irregular, floppy sort of flow we call turbulent flow. So let's look at our modern teapot and see whether this behaves in a similar way. Well, first of all, as soon as you pick it up, you realize that the center of gravity is going to be underneath your hand, whether it's in the unpouring position or the pouring position. And when it pours with a nice, pleasant, smooth flow. Whether you pour slowly or whether you really heave it up like that, it still pours nicely. Your first reaction when you pour rapidly like that is to want to put your thumb on the lid to stop it from falling out. But of course it's not going to fall out because it was designed not to. Designed, in fact, to be the right shape. Now, what has teapots to do with my own subject of electric motors? Well, just this. I think that looking at teapots has shown me that for the last few years, when I've been trying to design and develop new kinds of electric motor, all I've been doing is to change their shape. Or put it another way then, can we, simply by looking at shape, change our engineering tactics and make better use of our engineering materials? So let's now take another look at electric motors, simply from the point of view of their shape. Let's see first how it all began. Michael Faraday started with a disc, a copper disc, and a horseshoe magnet, which he put like that. He had brushes to collect the current at the edge of the disc and in the center. Now the next man said, why not put the magnet like that? And then another man said, no, let's put it at the edge like that, and then we can have a series of magnets all the way around. Yet another man said, let's put the magnets on the edge of the disc and make the disc into a cylinder, elongating it axially. They realized that this was going to make rather a large diameter motor, and so they said, well, let's fold the magnets over like that. And now, realizing that they were using the side of the poles rather than the front, they said, well, if you can do that, then you can put the magnets like that. And in this case, you can now put another disc here and then have another set of magnets and so on and make a long machine that way. So engineers between 1830 and 1880 were simply changing the shape of Faraday's disc to try to produce better electric motors and dynamos. In the Science Museum, we can see some of the extraordinary shapes that they came up with. In the same year that Faraday invented his disc dynamo, this machine appeared. And almost at once it produced a step backward, because it was suggested that the alternating current, which produces this flickering light, should be made more like battery current. And so at Ampere's suggestion, a commutator was fitted. The next machine also produced a step backward in a way. They added more magnets and more coils, and now realized that the magnets were heavy things to rotate, so they rotated the coils instead. Despite these steps backward, both these machines started off a topological explosion in which everybody tried all possible arrangements of magnets and conductor to try to make better use of this magic force that Faraday had discovered. Look at this machine, for example. This is the moving part, a sophisticated form of Faraday's disc with windings on it, and a magnet on each side of it. The magnetic field returned via the end pieces. One form of Faraday's disc. This is a more sophisticated version still, with more poles. This is the moving disc in the center. And then from this arrangement to one in which the magnets operated on the edge of what was still essentially a disc. Now, when these magnets were upright, in that position, it was realized that they would make a machine of very large diameter, rather ungainly, and so the magnets were folded back like that. But then, realizing the amount of space they wasted inside this machine, they went from this arrangement to this one. Now, in this machine of 1870, the horseshoe magnets dipped down in between a whole series of discs. When you look at the size of this mechanism and realize that the output of it was less than 2 kilowatts, then the shape just had to be wrong. One of the difficulties that designers of this period got themselves into was that they believed, quite wrongly, that you made better magnets when you made them long. So they finished up with all this wasted space through using these long magnets. And they made the same mistake with the previous machine, although in this case the magnets were arranged axially. But again, notice the long length of horseshoe magnet. But to appreciate the lengths that they really would go to, come and have a look at this next machine. Nearly 4 feet of electromagnet, and nearly all of it wasted. You see, the magnetic field generated by the coils at the top is going to leak across here all the way down, and very little of it will reach the base. Such was the obsession about 1880, which is the date of this machine, with magnetic length. Indeed, one author is on record as having said that it was always a good idea to let the magnetic flux have a good run at the air gap. But if you can forget all this top structure and concentrate on the business end, then the idea of having a pole at one side and an opposite pole at the other is not very different from the shape which 20 years later was to become the parent of the modern machine. This generator of 1900 has a pole at the top, a short pole, and a pole underneath. And the magnetic flux is returned by an all-embracing magnetic circuit around the outside. As soon as they'd done that, they realized they could put another pole at this side and another one here and make this rectangle become a circle. And once that circular shape with a magnetic circuit around the outside had been designed, then it did not change fundamentally for over 70 years. Here are 2 electric motors. This one built in 1914 and this one 50 years later. Now, in the intervening time, new developments in insulating materials for the electric wire and new magnetic materials for the magnetic poles have resulted, together with an increase in the cooling facilities in the small machine, have enabled engineers to produce this dramatic increase in the power available from a given size of motor. But inside, the shape of the 2 machines is the same. So as far as our modern electric motors is concerned, they're rather like our everyday teapots. They have evolved since 1880 rather than being designed. Each so-called new design has really been a copy of the previous one with a little addition. But suppose that out of curiosity or simply for fun, we decided to change the shape entirely, just to see what happened. Suppose we were to take our evolved cylindrical shape and do something fairly drastic to it, like slitting it open along one side and unrolling it. Then what have we done? It looks as if we might have produced straight line motion instead of the rotary motion we had before. And when we build a machine that looks exactly like that flat one, as this one is, then we shall find that we have done just that. Straight line propulsion. Man has thought himself superior to nature because he invented the wheel. And the wheel has certainly dominated his thinking in engineering through the centuries. But here is motion without a wheel in sight, linear motion. And there's a bonus to be had. If I increase the current to this machine, then I get lift as well as propulsion. And when I let go of the sheet, it simply flies through the air. Propulsion without wheels and without physical contact. Now, of course, there are all sorts of interesting possibilities for this kind of motion. Here's one of them. A Martian war machine inspired by H.G. Wells's War of the Worlds. When switched on, this machine will levitate itself above this aluminium sheet and also propel itself along. Switch on. Perhaps that's a bit way out at present, maybe the year 2000. But what is concerning us seriously at this time is the possibility of using the same idea, but for guidance along a track, for the possibility of high-speed travel. So let's now look at a levitation system which is only allowed to move in one direction. When this aluminium plate is lifted over this coil system, it will be seen to be free to move in this direction only. The only force resisting the motion is that of air friction, and at this kind of speed there's very little of that. Now once you're clear of the ground, there are only three practical methods that I know by which you may propel yourself along. First of all, you can, as it were, swim through the air. When this has been engineered, we call it an air screw. Of course, this involves a return to wheels with all their associated noise and atmospheric disturbance, but nevertheless, it's a method. But returning to a purely linear device, this one is called a moon rocket. I'll light it first and levitate it when it goes. Crikey. Well, you have something there on film that we hadn't thought of. Yes. Well, we'd better try that one again. I've only got one more rocket, I'm afraid, so I'd better make sure that this one is going to be screwed down a bit more carefully. I hope this one will be all right. All right, let's try again. Well, in an age when we think about pollution, I think you'll agree that this is not on. But a linear motor, of course, is another matter. And this small single-sided linear motor I'm going to use in conjunction with the levitation to produce what it looks at first sight to be an ideal system. It's got to have its own little aluminium strip to push against. So I switch the motor on, and then the levitation. See that again? The motor is still running. There's still some smoke coming from the motor. It's just because it's a very small machine. And talking of scaling up, unfortunately the levitation system doesn't readily scale up, because a full-size one would be too expensive in terms of power input and in terms of track cost. But the air cushion principle, which was invented by Sir Christopher Cockerell for hovercraft, can be married to the linear motor to produce what is called a tracked hovercraft. This is no model. This is the real thing. An air cushion vehicle running on a concrete track in Cambridgeshire. This vehicle is driven by a linear motor which is designed for speeds up to 150 miles an hour. Nearly 2 miles of track, so flat and straight that the eye can detect no flaws, is an impressive sight in itself. And this is the motor that drives it in course of construction.
Coils are being dropped into slots in a laminated steel core, and the whole motor is about 12 feet long. I'm going to show you just one or two of the problems that are associated with trying to make a high-speed linear motor. This block represents the iron part of the motor, or its magnetic circuit. And it's into the slots of this that we're going to put the electric windings. We might decide to put one in there and one in there, so as to make this a north pole and this a south. The question is, what fixes the speed of travel of the field? Well, if you're feeding the coils from 50 cycles per second supply, then the field will travel from there to there in a 50th of a second. And so you can work out the speed. And you see that the speed fixes the length of the coils. But we're not going to leave all these slots empty in between, because that would be a waste of good space. So we're going to fill them up like this with coils carrying different phases of current as indicated by the colors. Try and fill up each slot. And now it's becoming increasingly difficult to get this end into the slot. This end will go in all right, but this one, you see, is getting very tight indeed, because we're building up a bunch of end windings there. Now, this is a great drawback, because this part of the current is the useful bit, producing the thrust. This part is just waste. Not only is it waste, but it produces a magnetic field of its own, which does nothing except waste your applied voltage. Now, what length of coil would you need to have to produce a traveling magnetic field at 250 miles an hour? The answer turns out to be 4'6". So can you just imagine how these problems would be magnified when you have to deal with coils 4'6" long? You'd be putting one end in a slot over there and the other one 4'6" away over there. And then the next coil. And so on. And this end winding would have built up to something quite impossible by the time you'd filled all these slots. And that's as far as the electric circuit's concerned. Magnetically, all the magnetic flux through these teeth has got to find its way back up the core, and so the core has to be very deep. And so it seemed for a long time as though it was going to be absolutely impossible to design a 250 mile an hour motor to be fed directly from the mains, and yet not to use the mains was going to be very expensive. And then we started to think about shape first and the motor afterwards. And we realized that all the motors we've been making could be represented by a shape model, if you like, of that kind, showing that the magnetic circuits in red are in vertical planes, the electric circuits, or the coils, in horizontal planes, as shown by